Hello friends, in this lecture we will discuss about the American Standard Association system and orthogonal deck system. So before going to start this topic, let us discuss and know the basics or fundamental about the ASA and ORS tool nomenclature. So here we can see the statement of this ASA and ORSA. We can demonstrate and express the tool geometry in the form of machine reference system, that is also known as the American Standard Association, right? So we can say that geometry of a cutting tool refers usually to its several angle or slope of its silent working surfaces and cutting edge. There are various angles or slopes on the cutting tool, on the working surface and cutting edge. If you are looking the physical object, you can easily observe that these angles and the surfaces. So these angles are expressed with respect to some reference planes, and in the system and this system the three planes of reference and the coordinates are selected on the basis of configuration and axis of the machine tool concerned. So the planes and axes applied for expressing tool geometry in ASA system for turning operations are shown in figure. यहाँ पे आप फिगर में देख सकते हैं कि जो ये है फिगर, ये टर्निंग ऑपरेशन के लिए शो किया गया है फॉर द ASA सिस्टम, अमेरिकन स्टैंडर्ड एसोसिएशन सिस्टम के लिए, है ना. तो आप इस फिगर में देखें कि दिस इज द वेरियस सरफेसेस एंगल एंड द वेरियस पार्ट्स ऑफ दिस सिस्टम टर्निंग, दैट इज द सिंगल पॉइंट टूल for the turning in the hand system, right? So here this is the rake surface, this is the rake surface, and this is the rake surface. Second one is the, this is the auxiliary cutting edge. You can see that this is the auxiliary cutting edge, this is the tool nose, this is the auxiliary flank clearance surface, and next one is the principal cutting edge, and next one is the principal flank clearance surface. So there is the various parts of this single point tool for the turning in the tool hand system. Further, let us discuss about the various axes. You can see the various axes and planes for reference in ASA system. So here we can observe from the figure, there is a reference plane that is denoted by pi r, pi x, pi y, and xm, ym, and zm. So these are the reference planes and the coordinate used in ASA system for the tool geometry. So you can easily observe that from the given figure, that is the pi r, pi y, pi x, xm, ym, and zm. So these are the various reference planes, and this is the coordinates of the individual planes. If you are you can able to see, or you would like to visualize in the 3D coordinate system, so you can easily compare with the, or understand with this figure. So further, if we are moving further, where we can see that the pi r is equals to plane that will be perpendicular to the velocity vector. Second one, machine longitudinal plane pi x, that will be plane perpendicular to pi r and taken in direction of assumed longitudinal field. Next one is the pi y. Pi y is equals to machine transverse plane, that is the plane perpendicular to the both pi r and pi x. This plane is taken in the direction of assumed cross field. So you can notice from this figure, and you can correlate where is the pi r, pi x, and pi y, and how it is perpendicular from the to each other. Next, the axis xy, xm, ym, zm are in the direction of longitudinal feed, cross feed, cutting feed, respectively. So these are the direction of longitudinal feed, cross feed, and cutting feed velocity. And the main geometrical feature and angles of single point tools in the ASA system and the definition will be clearly observed from the figure. So further, after that, after understanding the various planes, these are the various angles of the ASA system. In this figure, we can see that the how the various angles are forming. So you can see that this is the gamma x, phi x, and this is the alpha y. These are the various angles that are making with respect to the individual planes. Now further, if you are moving for the tool nomenclature of American Standard Association, that is ASA, it utilizes three mutually perpendicular planes for reference purpose. Their name are machine longitudinal planes, machine transverse plane, and reference plane. And it consists of two rake angles, two clearance angles, two cutting edge angles, and the nose radius of a single point cutting tool. So these are the tool nomenclature for the ASA system that consists three mutually perpendicular planes for the reference purpose. Now further, the sequence of writing tool signature in ASA system. How could we write the tool signature in the ASA system? Right, with the name of various angles, with the name of various angles. So these are the, this is the table. From the table you can see that the gamma, this is the gamma y, gamma x, alpha x, phi s, and r. These are the notations for the ASA system of turning tool designation. And back deck angle should be 0 degree. Here back deck angle should be 0 degree. Now the side rack angle should be 5 degree in the ASA system. Back rack angle should be 6 degree. And next one is the side clearance angle, that should be alpha x should be 6 degree. And in end cutting edge angle should be 10 degree. Approach angle should be 30 degree. And nose radius should be 1 by 12, so inch. So these are the various ASA system of turning tool designations. So we have to remember for remember these values for the tool designations. Now further, if you are moving definition of rack angle shown in figure in ASA system, so we can say that side axial rack, that is denoted by gamma x, and it is the angle of inclination. It is the angle of inclination of rack surface from the reference plane pi r and measured on machine reference plane pi x. Now what is back rack? Back rack is denoted by gamma y, and angle, it is the angle of inclination of the rack surface from the reference plane, and that will be measured on machine transverse plane pi y. So you can notice from the above figure uh, about the pi y and angle of the back rack angle. Now next one is the clearance angles. So there is various clearance angles for the tool geometry. That is the side clearance, that is denoted by alpha x. Alpha x is the angle of inclination of the principal flank from the machined surface or CV, and measured, that will be measured on pi x plane. Pi x plane. Similarly, back clearance angle, that is denoted by alpha y, and it is the same as alpha x but measured on pi y plane. Now cutting angle should be the approach angle phi s. It is the angle between the cutting angles. There is various cutting angles. First one is the approach angle phi s, that is the angle between the principal cutting edge, its projection on pi r and pi y, and measured on pi r. Now what is the end cutting edge angle? It is the denoted by phi. It is denoted by phi, and it is the angle between the end cutting edge, its projection on pi r from pi x, and it will be measured on the pi r. Now next one is the nose radius r, that is denoted by r. That is denoted by r, and the unit of the nose radius should be in inch. Now further, if you are moving, r is the nose radius, and it is the curvature of the tool tip. It provides a strengthening of the tool nose and better surface finish. So these are the various parts of the tool geometry in the ASA system. Now further, if you are moving for the orthogonal deck system, that is ORS, so it is also utilized three mutually perpendicular planes for the reference purpose. First one is the cutting plane, second one is the orthogonal plane, and third one is the reference plane. So similarly to the ASA system, two signature in ORS system consists of two deck angle. It consists of two deck angles, two clearance angles, and two cutting edge angles and the nose radius of a single point cutting tool. So we can say that from the observation in ASA system, nose radius is measured in inch unit, and it should be measured in inch unit, and ORS system should be measured in the mm. So further, if we are looking in this table, the table shows that the sequence of writing tool signature in ORS system along with the name of various angles. So these are the various angles for the ORS system. First one is the inclination angle lambda, that it should be 0 degree. Next one is the orthogonal rake angle gamma naught, that should be minus 7 degree. Further, orthogonal clearance angle alpha naught should be 10 degree. Next one is the auxiliary orthogonal clearance angle alpha dash naught, that should be 8 degree. Next one is the auxiliary cutting edge angle phi 1 should be 15 degree, and principal cutting edge angle phi should be 60 degree, and r is the node radius, that should be 0.8 mm. So these are the ORS system for the of the turning tool designation, that is denoted by the various symbols. Now if we are moving further, we have to study about the tool reference system. So what is in that we will see that orthogonal rake system ORS. This system is also known as ISO old. The plane of the reference and the coordinates axis used for the expressing the tool angles in ORS system are pi r minus pi r pi c pi naught and x naught y naught z naught, which are taken in respect of the tool configuration as indicated. So these are the notations. Now further, this is the axis and planes of the references in the ORS system, and where we can say that reference plane pi r is perpendicular to the cutting velocity of velocity vector cv. Next one, the cutting phi c plane is perpendicular to the pi r. Phi c plane is perpendicular to the pi r, and it should be taken along the principal axis. This is the phi c. And next one is the orthogonal plane pi naught, that should be plane perpendicular to the both pi r and pi c and the axis. X naught should be along the line of the intersection of pi r and pi naught, and y naught is the along the line of intersection of the pi r and pi c, and z naught is the along the velocity vector normal to both x naught and y naught axis. So the basic geometry angles used to express the geometry of instrument in an orthogonal rack system should be, their definitions will be clearly shown in the figure. Now these are the tool angles in ORS system. From the figure you can easily observe that what is the tools angles, various angles are forming in this figure. So in the section cross sectional area we can easily identify that where is the, this is the phi, this is the gamma naught, this is the alpha naught, this is the pi naught, lambda. From the figure we can see that the tool angles in the ORS system, and we can see that from the figure orthogonal rake gamma naught, that should be the inclination of angle of inclination of the rake surface from reference plane pi r and measured on the orthogonal plane pi naught. Inclination angle lambda naught should be the, it is the angle between pi c from the direct of assumed longitudinal feed pi x and measured on pi c. And we can see from the figure clearance angle. Now further if you are moving, orthogonal clearance alpha naught of the principal flank. So what is the orthogonal clearance? So it is the angle of inclination of the principal flank from pi c and measured on pi naught. And what is the auxiliary orthogonal clearance pi naught alpha naught? So we can see from this figure and observe that it is the angle of inclination of the auxiliary flank from the auxiliary cutting plane phi c, and that will be measured on auxiliary orthogonal plane pi naught, and cutting angles we can see from the figure. Now further, principal cutting edge angle phi, it is the angle between phi c and the direction of the assumed longitudinal feed or pi x and measured on pi r. Next one, the auxiliary cutting angle phi 1. It is the angle between pi c and pi x, and that will be measured on pi r. So from the figure we can observe the various angles for the ORS system. And next one is the nose radius r. It should be in mm, and r is the radius of curvature of tool tip, right? So from the figure we can see that we can observe that the auxiliary orthogonal clearance angles for the cutting point tool. So I hope that you all have understood the content of the today's lecture. In the further lecture we will continue with the next topic. So thank you.